Hello everyone, welcome to the Intro to Stats review on definitions and descriptive statistics. So here you can see we have a review that we're going to go through together. So the first question says a blank is defined as a subset of a population. So this is just going to be our sample, right? Our sample is just some subset of our population. So if we have some population here, then our sample is just going to be some subset of that population, which we're going to find using our sampling techniques that we described. Number 2 says that for left skewed data, the median will be to the blank of the mean. So if you remember, left skewed means that our data has a tail going to the left, which if you recall, our mode should be wherever the peak is. And this data being to the left is going to pull our median down to the left a little bit. So we have our median. And then of course, these outliers that are way out here are going to pull our mean even further down. So in this case, this one would be that our median will be to the right of our mean. Number 3 says that population is to blank as sample is to survey. Well, a sample, to get a sample, we are going to take a survey. So to get population data, this means that we would need to take a census. Number 4, a blank measure is a measurement such that the random error is small. So this would be a reliable measure. Remember, a reliable measure is when our error is small between our different samples, right? So our random sample is going to be small, therefore we're going to have a reliable measure. A blank variable is characterized by gaps in the values. This would be a discrete measure, right? Because remember, discrete would be something like this, where we have these gaps. It could be whole numbers or could be decimals, but regardless, the idea is that you have these gaps that are some set amount and they are consistent, and also that we assume that there's nothing there. So this could be something like this is 1, 2, 3, 4, 5. Number 6, population is to parameter as sample is to blank. So for a population, if we're describing a characteristic about the population, we have a parameter. If we have a sample to describe a characteristic about the sample, this would be a statistic. Number 7, an experiment in which neither the subject nor the people administering the treatment knows what treatment they're receiving is a blank experiment. This would be a double-blind experiment. A single-blind experiment is when the person who is administering the treatment knows whether they're getting the placebo or the treatment, but the patient does not. A double-blind is when neither of them know whether they're receiving the treatment or the placebo. Number 8, data can be one of 2 types, blank or blank. Now, this one is actually a little bit ambiguous because it could be asking about whether the fact that data could be qualitative or quantitative, meaning that it is non-numeric and more of a categorical variable, and one that is numeric with some numeric meaning that can be actually used, for example, addition, averaging, things like that. Or it could even be the fact that it's discrete versus continuous. I believe this one, though, we're going for qualitative versus quantitative. Define and give 2 examples of a discrete variable. Okay, so a discrete variable could be something where I'm using count data. For example, if I go into a parking deck and I start looking at the colors of the different cars. So I start counting 1, 2, 3, right? There's 8 yellow cars, there's 6 green cars, there's 4 red cars. This would be a discrete sample because what I'm doing is I'm counting them, meaning that there's a gap, right? I either have 1 red car or I have 2 red cars. I have 2 red cars or I have 3 red cars. I can't have 3.2 red cars. Another example of this could be if I'm, at a grocery store and I'm counting inventory. Things that have whole numbers, pretty much always going to be discrete because we are counting them. So countable numbers are always discrete. Now you may have examples that are actually continuous, but when we measure them as discrete values. An example of this might be something like if I'm taking a temperature using a digital thermometer that only goes down to 1 decimal. This would be a discrete measure, right? 90 degrees, 90.1 degrees, 90.2 degrees, 90.3 degrees. In each one of these cases, I would have a gap of 0.1. So while the measurement temperature is actually continuous, the way I would be measuring it would be using a discrete measurement. Next, we want to define and give 2 examples of a continuous variable. Well, if a discrete measurement is one that has gaps with nothing in the gaps, a continuous measure would be one where there is no gaps that exist. It's a number line or a continuum, which means that all values are possible. This means that between any 2 values, let's say 0 and 1, that there will be an infinite number of values. So I could split this in half. Let's say we go to 0.5. And then I could split this in half, 0.25. And I could split this in half, 0.125. And I could split this in half, and I could split it in half. And basically every single point, I could always find another point between that exist because there's an infinite number of them. So examples of continuous variables would be things like temperature, weight, height, time. These are all things that have a continuum where starting at some point 0, I have some distance that I've covered, and there's technically an infinite number of values that I've hit between any two of them. Number 11, what is the difference between an observational study and an experimental study? So an observational study is one in which the experimenter does not impart any experimental conditions or treatments on the participants. So this could be something like if I'm observing something in nature and I'm not actually imparting any sort of treatment, or it could be even something like giving a survey. I'm asking you questions to know what your views are, but in the end, I'm not actually putting any treatment into the subjects that I'm looking at. I'm just asking them questions, getting the answers. An experimental study is one in which researchers do impart some treatment. This could be something like a medical trial, or it could be something like if I'm giving students an exam and one of my classrooms, I crank up the temperature to see how being agitated affects test conditions. In this case, the treatment was me changing the temperature. So while other classes are taking it at a normal temperature, my treatment group would be the ones who are getting the treatment, in this case, the higher temperature in the classroom. Number 12 asks, what are the 3 characteristics for a well-designed experiment? And it briefly explained why each characteristic is important. So our 3 characteristics are control, randomization, and replication. So briefly, to kind of describe what each of these are, is that the first step is that you want to have some sort of control in your experiment. That means that you should have some treatment group or groups and a control. This would be your group that you're comparing them to, so that way we can see if, even though if I see an increase based on my treatment, this would allow me to have something to compare it to see would all people be getting an increase because of outside factors, right? Those confounding variables that I really didn't take into account, or is it specifically because of my treatment? This is why we need that control. The second one is randomization. When I'm putting people into their groups, control, treatment 1, treatment 2, whatever my groups would be, I use randomization so that I'm preventing any bias being created by me by how they get put into their groups. Because remember, anytime you are making a decision or setting some sort of rule in place, you are in fact imparting some bias anytime you as a researcher make a choice, right? And what that choice is would determine how you're biasing that study. So instead of me picking which group everyone goes into, I would put them into a computer. I would randomly select, let's say, half of them to go into the treatment, and anyone who didn't go into the treatment would automatically go into the control group. And the last one is replication. Replication is redoing an experiment under the same or similar conditions. This allows us to kind of verify whether the results seem to hold or whether it might actually refute our results. And the more times we can do an experiment under the same or similar conditions and it verifies it, this would strengthen the case that our experimental conclusions are actually correct. Number 13, determine which sampling technique is used in the following cases. A study is being conducted to see how Head Start education reforms are working in a state. Out of 11 school districts, 7 districts are selected, and every student within the selected districts are included in the study. This would be cluster sampling because we have our different districts, District 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and we are specifically choosing we had chose 11, so we have a bunch more, but we're choosing 11. So we're choosing entire districts, and we're selecting everybody within those districts. So this would be a cluster sample. Part B says, noticing that the prior study was not very representative, the researchers decided to run a second study where students were grouped by school district, and then students were selected at random from these 11 school districts. So in this case, in each of these school districts, you have all the students that make up the district. And we are using some method, didn't specify, but probably simple random sample within the districts to select specific students. This would be stratified sampling because we are breaking the individuals into stratum, their school district, that would be the groups that they are a part of, just like we did clustering, except now what we're doing is to get some representation between every group, we're simple random sample within each stratum in order to randomly select our sample. Part C. While the second study was more representative, the researchers decided to do a third study and want to limit bias from their sampling technique. They assign every student in the state a number and randomly select students. So this would be a simple random sample because what they're doing is they are giving everybody an equal probability of being selected and then selecting from all possible students using probably a computer random number table. Now, one thing I want to point out is I want to remind you all that a random sample is not the same as a simple random sample. A random sample is the ideal of a sample that you do not impart any bias by your sampling technique. A simple random sample is an actual method of doing it where every possible person that can be selected is put into like a list or given a random number. And then we use random number generation to select who is going to be included in our sample. Now, the reason that a simple random sample, while imparts very little bias, is not completely unbiased, this is because we do have to make one decision. Are we going to do this sampling with replacement or without replacement? If we do with replacement, then we are actually going to have the chance that we are going to get the same person 2, 3, however many times, right? Because it's random, meaning that we would either have a smaller sample than we wanted, or we would have to increase the sample size, getting more people, but also, having to account for the fact that we're having repeats. Therefore, we're adding some bias. If we chose to do it without replacement, meaning when someone is selected, they're taken out, then again, we've added some bias because as we're going through picking the next person, right? Because there's no way you can actually pick all the people at the same time. Even if you're using a computer, you're still technically picking one person, taking them out of the list. Now you have one less person. So if I have 500 people, first person has 1 out of 500 chance of being selected. I pull that person out. Next person has 1 out of 499 chance of being selected. Pull that person out. So technically, everybody has an equal probability of being selected. So a simple random sample is not a random sample. It is the closest we can get to physically getting a random sample, but it does have some little bit of bias based on our method of with replacement or without replacement. For our next problem, we have the length in pages of the 10 best-selling books of 2020 on Amazon. So you can see the number of pages here, and I've got it written already here. And it wants us to find the mean, median, and mode of this data. So the first one I'm actually going to do is I'm going to do the mode, because the mode is the simplest, where all we're doing is we're looking for what value occurs most often. So we have 768, 240, 384, 84, 672, 352, 34, 192, 320, and 592. So looking at this, it doesn't look like I actually have any repeats. So in this case, you could say that there's no unique mode or that there's no mode probably, because even though technically every value occurs most often, that really doesn't give us any extra information. So in this case, I would say no mode exists. But I'm actually hold off on writing that down until I've done the median, because to do the median, I first need to order the data. At that point, it'll be a lot easier to see if I have a mode because the two data points will be next to each other if they're the same. So for our median, we first need to write these in order. So it looks like our lowest value is going to be 34. So I'm going to just mark this out here so I don't forget it. And then it looks like our next value is going to be 84. Got some pretty short books here. When I made this data, it was just randomly made data, but we're pretending that these represent the pages of books. The next one is going to be, it looks like 192. And then we have 240. Then we have 320. Then I have 384. Next I have, I missed 352. This is why we gotta leave a little space there. Next I have 592. 672, and 768. Now, when you're doing this, what I would suggest you do, as you're kind of writing these out in order and marking them off your original data, is just count your first number of data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. and then count your reordered values. And again, with median, it could be ascending or descending order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There. It looks like we didn't miss any data points. So now we have them in ascending order. So again, going back to our mode, you'll notice that we do not have any repeats. So now I'll write that there is no mode. Now for our median, because we have n equals 10, if we were to take this 10 and divide it by 2, we're going to get the value 5. Now remember, if we have an even number of our sample, this means that when we count over 5, it's going to be 5 and then the next value 6. Or if we count from the top and we count 5 in, it's going to be the 5th value coming in from the top and then the next one. If we had an odd number and we got something like 5.5, in this case, that would just be the number we select. We go up to 5 and then it would be the next number. But specifically in our case, we had 10 divided by 2 is equal to 5. So I'm going to go over and say 1, 2, 3, 4, 5. So it's going to be this value here and this value here. And notice it works whether we go from the top as well. 1, 2, 3, 4, 5, and then the next number. So it's going to be the average of these two numbers. So we take 320 plus 352 divided by 2. So in this case, we're going to get 672 divided by 2. So this is going to be equal to 336. So this is going to be our median. It's like we have a point that is, of course, it would be the point that I missed. We're going to have a point right here between these two, which is what splits our data. 1, 2, 3, 4, 5. And from the other side, 1, 2, 3, 4, 5. So 336 would evenly split all of our data right down the middle. Now, let's do our mean. So for our mean, we don't have to order our data. But I'm going to use our ordered data just because I already wrote out all the non-ordered data. But mean doesn't matter about being ordered. But the data is the same, so I'm just going to use it. So to find mean, this is going to be x bar is equal to the sum of our x's divided by our sample size. So in this case, what we're going to do is we're going to take the sum of our sample, which is going to be 34 plus 84 plus 192 plus ... up to 768. And then I'm going to divide it by how many numbers are on my sample, which we said was 10. So I'm going to divide this by 10, and let's see what I get. So I got 363.8. So based on this data, I have no mode, I have a median of 336 and a mean of 363.8. Now, just as a reminder here, mode is not really affected by outliers. Median is not really affected by outliers, but it is a little bit because if I add any data points to one side, it will shift slightly in my data. Mean, on the other hand, is very affected by outliers, which in this case, you'll notice that we have values that go from 34 up to 768. But if you look in general, it looks like most of the data is somewhere in the 200 to 600 range, meaning that this 34 actually might be an outlier. We'd have to check, but either way, it's going to affect where our values are. Now, I actually could kind of look at that to determine whether I have a skewed left or right by the fact of my median is less than my mean. So if I do have any skew, if you remember, this would mean that if my mean is greater than my median, this would mean that I have right skewed data. So in that case, actually, it looks like the skew might be to the right. So the 768, if we had an outlier, it might be that value. Part B, which measure of central tendency best represents the center of the data? Explain in 1 or 2 sentences. Now this one, I would argue that median, if you're ever just using central tendency to describe the data, I think median is the best way to talk about central data because it will be where the actual center of the data is. Half the data points are to the left, half the data points are to the right. But if it comes down to any sort of calculation and things like that, generally we're going to err towards using mean because it's easier to use and it's easier for a lot of people to understand. And one of the nice things, and we'll talk about this more later on, is the fact that if I have symmetric and normally distributed data, then mean is actually going to be equal to mode. So if I have symmetric data and I have enough of it or it's normally distributed, then in this case, it's really not going to matter. But if I'm just talking about the data, I generally would go with median because it's where the center of the actual data is. So I know that 50% of the data points are below, 50% are above, and I know that it's not heavily affected by outliers. In this next problem, we have the ages in years of a random sample of students in a campus dining hall. They are 19, 20, 17, 19, 17, 21, 23, 21, 17, and 17. And wants to know what is the standard deviation. So the standard deviation is just going to be S, because I'm assuming that this is going to be sample data, and it even says we have a sample of students, so it is. The sample standard deviation is going to be each of our X values minus the mean of our data squared divided by, because it's a sample, we're going to divide by n minus 1, and then we will take the square root of the entire thing. Now, to do this, we have all of our data points, the 19, 20, 17, 19, such like that, but first we need to figure out what our mean is. So if you remember, our mean is going to be the sum of our X values divided by our sample size n. So this is going to be 19 plus 20 So for this, I got 19.1. So now in order to find my sample standard deviation, what I would need to do is first, I need to find how much does each data point deviate from the mean. So this is going to be 19 minus 19.1, 20 minus 19.1, 17 minus 19.1. Do this for each of our data points. Then I'm going to take each of those and I'm going to square it. I'm going to add up all of these, forgot to put my summation here. And then I'm going to take the sum of all of those deviations that are squared, so sum of squared deviations, or sum of squares, and then I'm going to divide by my sample size, 10 minus 1, and then I'll take the square root of that. So to write this out, this would be 19 minus 19.1 squared plus 20 minus 19.1 squared plus 17 minus 19.1 squared plus dot 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 up to 17 minus 19.1 squared divided by n minus 1, which would be 10 minus 1 or 9, and I'll take the square root of the whole thing. So give me a second, I'll calculate that. I'll be right back. Okay, so now for this, I got 2.32857. So on our test, you'll see at the bottom here, it says we're just going to do 2 decimal places. So in this case, we would actually just put the final answer 2.33. So you'll notice to do this, what I did is I took every data point we had, 19, and I subtracted our mean that we calculated, 19.1, and I squared it. And then I took the next value, 20, and I subtracted my mean, 19.1, and I squared it. And I take my third data point, 17, minus 19.1, and I squared it. I did this for all of them. I added them all together, and then I got 48.8001. Then, underneath the square root, you would take that value, divide it by 9, and then take the square root of the entire thing to get this value, if you're using your calculator, in which case we would then just round to 2 decimal places, we get 2.33. For our next section, we have some true or false questions. And then if we have any that we answer as false, we'll just answer what the actual true value is. So number 16, in a frequency distribution, the class width is the distance between the lower and upper class limits of a class. So this one is actually false. The class width is the distance from the upper class boundary and the lower class boundary. So if you remember, if we are using class limits, the way we find class width using class limits would be the distance from the upper class limit minus the lower class limit plus the tolerance. So in this case, it would either have to be plus the tolerance, or it would have to be the upper class boundary minus the lower class boundary to make it a true statement. Number 17, the difference between 2 consecutive midpoints is equal to the class width. Now this is actually true because if you think about the fact, let's say I have these classes here based on class boundaries, if I have some midpoint here and some midpoint here, this distance would be the same as if I looked at the distance between my class boundaries. Number 18, the graph of a cumulative frequency should always decrease from left and right. So of course this one is easily false because remember, a cumulative frequency is non-decreasing. It can increase or it can stay the same, but it will never decrease. So this one should be that it will always increase or not, should be non-decreasing. This is why one, you can't just change it to increase because technically it can also stay the same. Number 19, class boundaries ensure that consecutive bars of a histogram touch. And this is true. Whenever we have our initial frequency table, we have class limits, which means that every class will actually have a gap between them. So this might be the interval for first group, this would be the interval for the second class, this would be the interval for the third class, and we take this distance between them, the tolerance, and we subtract half the tolerance from the lower class limits. We take half the tolerance and we add it to our upper class limits, and now they will be class boundaries. So when we have class boundaries, then yes, that means that our intervals are in fact touching. Therefore, we would have a continuous line versus having any sort of gaps, because a histogram has to have no gaps. The mean is the measure of central tendency most likely to be affected by outliers. This is true because, as we talked about previously, median is barely affected by outliers. It just treats it as one extra data point above or below. And mode does not care about outliers at all unless somehow it changes what occurs most often. And usually it shouldn't, because the fact is that if it's an outlier, it's supposed to be something that is outside what you would expect for the data in general. For problem 21, we're given a list of GPAs of 20 students, so 1.8, 2.2, 2.6, up to 2.2. We want to complete this frequency table and identify the class width. So in this case, I've already written out the partially filled out table. Now it's partially filled out because if you look here, we do actually have one of the classes, meaning that if we wanted to, we could actually figure out what the rest of the classes are just by using this one piece of information here. So you remember in our example we did previously, we used whole numbers. And I told you that if you wanted, you could kind of just count them if it's not a very big interval. Well, we could do the same thing here because looking at this data, the fact that I have tenths for my values, this means that I'm going to have a tolerance of 0.1, meaning that if I were to count, instead of thinking of this as 2.3 to 2.7, think of it like you would count from 23 to 27. So you'd be 23, 24, 25, 26, 27. So I could do the same thing using 0.1, 2.3, 2.4, 2.5, 2.6, 2.7. So in this case, I have a class width of 0.5. But let's say that we wanted to be a little more precise about it. Or if you remember, what we could do is we could use the upper class limit minus the lower class limit plus the tolerance. So our class width is going to be 2.7 minus 2.3 plus 0.1. Wait, did I count that wrong? 2.3, 2.4, 2.5, 2.6, 2.7. If I do 2.7 minus 2.3, oh, that would give me 0.4 plus 0.1 equals, 0.5. Okay, so this matches the class width we got. Now, depending on what information we gave you in the table, whether we gave you 2 consecutive class limits or we had class bounds or anything like that, midpoints, there's a lot of ways you can find class width. So we can do that right away. That's the first part, we're done. So now what I'm gonna do is I'm gonna fill out the rest of the table. So when I go to the next interval, remember I'm gonna go up by my tolerance. So if I have 2.7 plus my tolerance of 0.1, this is gonna give me 2.8. And I'm gonna do 2.8, 2.9, 3.0, 3.1, 3.2. Go up by 0.1, so this is going to be 3.3, 3.3, 3.4, 3.5, 3.6, 3.7. Now let's say that you had a bigger interval and you didn't want to count using your fingers. Remember, what you can always do is, likewise, when we went from using our class levels, our limits, to find our class width, we had to add our tolerance. You would do the same thing, but you would subtract your tolerance. So for example, if I went to 2.8, it would be plus 0.5 minus 0.1. So 2.8 plus 0.5 would give me 3.3, minus 0.1 would give me 3.2. So in this case, it would just be your class width. So if you started with your lower class limit, it would be your class width minus tolerance. And you could add that to it, and that would give you your upper class limit. So let's do that for this one. We're going to go backwards though. So I have 2.3. I'm going to go down to the next level. So this is going to be 2.2. And then I need to go down by my class width minus the tolerance. So 0.5 minus 0.1 is 0.4. So 2.2 minus 0.4 is going to give me 1.8. And then let's just double check. 1.8, 1.9, 2.0, 2.1, 2.2. There we go. We have our intervals. So next step we need to do, we need to use our listed data and we need to tally in to determine what our frequencies are. So in this case, I'm going to start with 1.8, so I'd put a little tick mark here. Next one, we have a 2.2, so I'll put another tick mark here. Then we have a 2.6, that's going to be a tick mark here. We have a 3.4, that's going to be a tick mark here. While I was trying to put this data in, I actually noticed a mistake. I noticed that I had values that were falling outside of my last interval. Well, if you look at the original problem, you will see that below the interval that was given, there were 3 intervals. I only drew 2, which means that we actually didn't have the last interval. So now I'm going to add that now. So this is going to go up to 3.8. So 3.8, 3.9, 4.0, 4.1, 4.2. Now, the reason I knew that there was a mistake is because, remember our rules for histograms. 1, there can be no gaps. Well, we have no gaps once we get to our class boundaries. But also, it has to be exhaustive, meaning that all of the data we have has to fall into one of our intervals. If you look at the data that was given with the problem, we had 2 4.0s. Well, if I didn't have this interval here, this would fall outside of my intervals, meaning that either I made a mistake in my intervals, which I didn't. Oh, I did because I didn't have one of them, but let's say that I had all of them. That would mean that I either messed up my class width or I messed up how I wrote my intervals. This is how I knew that there had to be a mistake. So now what I'm going to do is I'm going to go tally for all of our data points. So the first one is 1.8, so I'm just going to put a little check mark there. Then I have a 2.2, so another check mark there. I have a 2.6. I have a 3.4. Next is 3.5. Next is 1.9. Okay, I've gone through all the numbers and it looks like it was actually missing one in the interval 3.3 to 3.7. So there actually should have been a frequency of 8 there. So now what we're going to do is we're going to find our class midpoints. So if you remember, midpoint is just going to be the average of your 2 values in your interval. That means that if I want my midpoint, this is going to be equal to, in this case, I'm going to add 1.8 plus 2.2 divided by 2. This is going to give me 4 divided by 2, which is going to be 2. Now, because all of these intervals should have an equal width, and they do because I set them up that way, this means that I can actually use the pattern where if I look at this 2, it is 0.2 away from my lower class limit, or 0.2 away from my upper class limit. I can use either one. So this one's going to be 2.3 plus 0.2, which is going to be 2.5, 3.0, 3.5, and 4.0. Now what we're going to do is we're going to find our lower class boundaries and our upper class boundaries. So if you remember, what we're going to do is we're going to take, for our lower class boundaries, our lower class limits and subtract half of the tolerance. So this would be half of 0.1, which would be 0.05. So this is going to be 1.75. This one's going to be 2.25. This one's going to be 2.75. This one's going to be 3.25. And this one's going to be 3.75. Then for our upper class boundaries, we're going to do the same thing, except we're going to add half the tolerance, so 0.05. So this is going to be 2.25, 2.75, 3.25, 3.75, and 4.25. And this is a good place to double check, make sure you didn't make any mistakes, because your upper class boundary of one group should be the same as the lower class boundary for the next group. So now we have our frequencies, we have our midpoints, we have our class boundaries. At this point, you could draw your histogram for either frequency with midpoints for your x-axis or class boundaries for your x-axis. Next, we're going to find our relative frequency. So our relative frequency, if you remember, is just going to be the frequency of whatever interval I, that's my index, divided by the sum of the frequencies. Now we have a percent sign here. That means that we're going to take whatever we get and we're going to multiply it by 100. So this means the first one, I have a frequency of 4. 4 out of my total of 20. I had a total of 20. So 4 out of 20 is the same thing as 2 out of 10, meaning it's going to be 20%, right? It's multiplied 0.2 by 100, and I'm going to get 20%. The next one, 3, is going to be, well, if 4 is 20%, that means that every one frequency is worth 5%. That means this one's going to be 15%. This one's going to be 15%. This one is going to be 40%. and this one is going to be 10%. And then if we were to sum these up, they should sum up to 1 if you're using decimals, or 100 if you're using percentages like we are. So 40, 50, 65, 80, 100. So this is a quick place you can double check. Looks like our relative frequency is good. Our cumulative frequency, if you remember, it is going to be the frequency of that specific interval plus any preceding intervals. Your first interval is always going to be the same as the initial frequency because there's nothing that precedes it. So in this case, it's going to be 4. Then we have 3 plus what came before it. So 3 plus 4 is 7. Then we have 3 plus 7, which equals 10. Then we have 8 plus 10, which is equal to 18. And then the last one, we have 18 plus 2, which is going to give us 20. Again, this is another place you can double check. You can always make sure this should always be the same as your total frequency. Now, sometimes we will actually have another column, which is going to be the cumulative relative frequency. If you have the cumulative relative frequency, what you could do is you could take these cumulative frequencies and you could find the relative frequency of them like before. So you'd get 4 over 20, and then we do it, if we want to do it as a percentage, times 100, which would give us, again, it would give us 20%. 7 over 20, which would give us 35%. 10 over 20, 50%, 18 over 20 would be 90%, and then 20 over 20 would be 100%. Or you could go to your relative frequencies and you could create a cumulative frequency of them. So the first one would be 20, then 20 plus 15 gives us 35, 35 plus 15 gives us 50, 50 plus 40 gives us 90, 90 plus 10 gives us 100%. In problem 22, we have a market researcher wants to calculate the average price for 5 different products that are sold at a store. The prices and the numbers of units sold are as follows. We have product A has a price of $10, units sold is 30. Product B, $15, units sold is 20, $20, 50, 25, 40, and 30, 10. We want to know what is the average price of the units sold. Now, this is going to be a weighted mean. So if you remember, our weighted mean is going to be X bar is equal to the sum of our outcomes X times their associated weight divided by the sum of our weights. So the first thing here is to determine what is our weight, the price or the units sold. And in this one, it's a little bit ambiguous, but it's going to be the price. And this is because the weight is sort of how much does it affect the total average. So for each product A that I sell, I am increasing by $10. For each product B I sell, I'm increasing by $15. For each product C, it's $20. So this is actually the weight. How much is that product worth, right? Because if I sold product F, this is 3 times more valuable than selling a product A. I would have to sell 3 of A to get the same value as product F. So in this case, my weights are going to be the price. So now if I wanted to do this, this is going to be the price and the units sold. So the units sold, so 30 times 10 plus 20 times 15 plus 50 times 20 plus 40 times 25 plus 10 times 30. And then I have to take the sum of my weights. Remember, the weights are the prices. So in this case, it's going to be 10 plus 15 plus 20 plus 25 plus 30. And there should be a total of 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Looks good. So now all I have to do is I just have to do this calculation really quick. And I get a total weighted mean of 29.0. So this is the weighted mean. This means that on average, when I sold my products, they have an average value of each sale would be 29. Okay, so that is how we do a weighted mean. It's just the sum of each outcome, how many were sold, times the weight, what was their price, divided by the sum of the weights. What was the total price if you were to put it all together? For our last problem, we're going to be doing what we like to call the table calculations problem, where we're going to fill out our table, which is going to have our sum class. In this case, it was minutes that people were doing something. It doesn't really matter for the actual calculations. Frequency, we need to find the midpoint. We need to find the midpoint times the frequency. And then from there, we're going to find what our mean is. We'll go to the next column in the table, which is going to be our midpoint minus the mean. We'll take each of those values. We'll then square them for the next column. We'll take each of those values, multiply them by the associated frequency, and we'll fill out the rest of our table to get our sum of squares. From there, we can figure out what is our variance and what is our standard deviation. So I actually pre-filled out the table here. So this problem, we gave you just the intervals and you had to actually go with the data and figure out how many were in each. I just skipped that step and now we're at this point. So the next thing we need to figure out what our midpoint M is. So if I have 71 and 90, to find my midpoint, well, all I'm going to do is I'm just going to add up 71 plus 90, and I'm going to divide by 2. And I'm going to do this on the calculator just to make sure I don't make any silly mistakes. So 80.5. So remember, they should all have the same width. So the fact is this went up from 71 to 80.5. This one is going to go from 91 to 100.5. This one's going to go to 111 to 120.5. This one's going to go from 131 to 140.5. Now, you don't have to put any total here because it really doesn't make any sense. The total is just for when we're doing our actual calculations. So next thing we're going to do is we're going to find our midpoint, which if you took my class with me, you obviously know a lot of times I'll just put X here because it's an outcome, but we're doing M for midpoint to keep it uniform. So we're going to take this midpoint, 80.5, and multiply it by this frequency of 4. And this is going to give us 322. Next, we're going to take that 100.5, and we're going to multiply that by 4, which, yes, I could do this in my head, but I'm just going to use a calculator because I don't want to make any mistakes and then have to go back and erase a bunch of stuff. Next is going to be 120.5 times 8, which is going to be 964. And next one, we're going to have 140.5 times a frequency of 9. This is going to give us 1,264.5. And now I'm going to take the total of these midpoints times frequencies. So I'm going to have 322 plus 402 plus 964 plus 1,264.5 for a total of 2,952.5. Now at this point, our next part of our table, we're looking for M minus X bar. Well, we don't know what X bar is, so this should be your indication that you need to now find your X bar. So to find our mean, we have X bar is just going to be equal to the sum of our midpoints times the frequency divided by the sum of our frequencies, which don't forget, you can always just write this as N if you know what the sample size is. So here we have the sum of MF, that's this right here. So we're going to take this and we're just going to plug this in. And we have the sum of our F, that's this. We're just going to plug that in, and this is going to give us 2,952.5 divided by 25. So we're going to get 118.1. So now we can do this step. We can take each of these M's and we can subtract 118.1. So I'm going to have 80.5 minus 118.1, which is going to give me negative 37.6. Now I'm going to take 100.5 and I'm going to do the same. And I'm going to get negative 17.6. Next, I'm going to take 120.5 and subtract 118.1, and I'm going to get 2.4. And last, I'm going to take my 140.5, and I'm going to subtract 118.1, and I'm going to get 22.4. Now, the reason we need to square these terms next is because if we were to take the sum of these, taking into account the frequency, so we took negative 37.6 times 4, negative 17.6 times 4, 2.4 times 8, 22.4 times 9, we were to sum all these up, they should basically cancel each other out to around 0. So we're going to take each of these values. The next part of our table is going to be M minus X bar squared. So we're going to take each of these values and we're going to square it. So the first one is going to be 37.6 squared is going to be 1,413.76. 17.6 squared is going to be 309.76. 2.4 squared is going to be 5.76. And then 22.4 squared is going to be 501.76. And then the last step for our table, we're going to take this midpoint minus our mean X bar squared, so this value, and we're going to multiply it by the frequency. So in this case, we're going to take this 1,413.76, we're going to multiply that by 4. So 1,413.76 times 4, I'm going to get 5,655.04. Then I'm going to take 309.76, and I'm going to multiply that by my frequency 4. This is going to give me 1,239.04. Next, I'm going to take that 5.76, I'm going to multiply that by my frequency of 8. This is going to give me 46.08. And then I'm going to take that 501.76, I'm going to multiply by that frequency of 9. This is going to give me 4,515.84. And then I'm going to sum all these up, and I'm going to get 4,515.84 plus 46.08 plus 1,239.04 plus 5,655.04, and I'm going to get a total of 11,456 on the dot. So that actually is really nice. So 11,456. Now, if you remember, this is our sum of squares, which we oftentimes will just write as SS. So next thing we're going to do is we're going to find either our variance or our standard deviation. So I'm going to do variance just because I can find the standard deviation just by taking the square root of it afterwards. So we have sample data. This means that our variance is going to be S squared equals X minus X bar, so the deviation of each data point from our mean, squared. And of course, we have to take into account that we're going to sum all these up, including the frequencies, because we have to take into account the fact that whenever I find this deviation of negative 37.6, well, there's 4 of them. It's not just a deviation of negative 37.6, it's 4 deviations of negative 37.6, 4 deviations of negative 17.6, 8 deviations of 2.4, and 9 deviations of 22.4. So that's why we have to multiply by our frequency after we've squared the terms. Then I'm going to divide by my sum of my frequencies minus 1. So this top term is just our sum of squares. It is, so in this case we used m, so I'm just going to correct this real quick just so that it doesn't throw anyone off. It is m minus x bar squared times the frequency, sum. That's this value right here, the sum of squares. So this is going to be 11,456 divided by the sum of our frequencies, which is 25 minus 1. So divided by 24. This is going to give us a standard variance of 477.33. And the last part of the problem is, okay, now I want the standard deviation. So rather than rewrite out this entire formula, which I could just take the square root of the sum of m minus x bar squared f over the sum of f minus 1. Or I could just say, well, if I want the standard deviation, it's just going to be the variance, and I'm going to take the square root of that. So that's exactly what I'm going to do. I'm going to take the square root of 477.33, and I'm going to get a standard deviation of 21.8479, so I'm going to say 0.85. And therefore, we've finished it up. We've completed our entire table. We have our sum of squares. We had to figure out our mean in order to actually figure out the second half of the table. We figured out our variance so we have what we're solving for, our formula, we plugged in, we got our answer, and then we did the same thing for standard deviation. The only difference is we changed our formula. Instead of writing this with the square root under it, we just said, well, if we already know what this is, it's just the square root of this. So our formula became the square root of s squared, plugged in, got our answer. And that's it for our review. So if you followed along with this should be everything you really kind of need for our upcoming test, and I hope this helped. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.